What are confidence intervals and how to interpret them? This video focuses on 95% confidence intervals for mean differences in research situations when you're using one sample mean. Specifically in this video, I'll describe what confidence intervals are, and then I'll describe the different types of confidence intervals that exist. I'll define important terms, and I'll conclude by performing a specific example using a z-curve and a second example using a t-curve. A confidence interval is an estimated range of plausible values for a population parameter. All confidence intervals can be constructed to have varying levels of precision or confidence. Commonly used levels of confidence are listed here. This video will focus on constructing 95% confidence levels. Different kinds of confidence intervals estimate different kinds of population parameters. One of the most common confidence intervals is one that estimates a population mean. Another very common confidence interval is a mean difference confidence interval, which tries to estimate the difference between two populations. This video is focusing on mean difference confidence intervals. As is reflected here, there are several different ways to compute a mean difference confidence interval, and it really depends on the research situation you have in front of you. Here, we're going to focus on two very specific research situations. Both of them, you have one sample mean and one population mean. The only difference is in one situation, you know the population standard deviation, and in the second, you do not know the population standard deviation. Before diving into some examples, it's important that you understand some key terms. A point estimate, as you will learn in the next few slides, is the most plausible value for a population parameter. And a margin of error is a range of values extending above and below the point estimate. And that margin of error is going to vary based on the sampling error in the study and the level of confidence or precision that you desire in your estimate. In both of the examples in this video, we're going to be using a sample mean to represent one population and a population mean to represent the other. And we're trying to estimate the difference between these two populations. And the point estimate is going to be the difference between the sample mean and the population mean. The margin of error is going to be computed using two terms. The Ci value, which again is determined by the level of confidence or precision you want your estimate to have, and then the amount of sampling error that is expected in that study. By applying the margin of error to the point estimate, you'll get the upper bound and the lower bound of the confidence interval. Simply add the margin of error to the point estimate to get the upper bound, and then subtract the margin of error from the point estimate to get the lower bound. Remember, what you're trying to do is trying to find the range of plausible values for the mean difference between the populations. The upper bound value is the largest plausible mean difference, and the lower bound is the smallest plausible mean difference. The point estimate will always be exactly in the middle of the upper bound and lower bound values, and it is always considered the most plausible mean difference between the populations. Now that you understand the terms point estimate, margin of error, and upper bound and lower bound, we're ready to perform an example. In this research situation, we're trying to estimate the mean difference between two populations, specifically a population of trained workers and a population of untrained workers. We take one sample of 100 trained workers, and they make a sample mean of 25 errors per month. We know that the population of untrained workers make an average of 26.5 errors per month, with a standard deviation of 10 errors per month. We're going to be using a z-curve here because we know the population standard deviation, or sigma. First, we compute the point estimate. The sample mean minus the population mean gives us a negative 1.5. This is the most plausible mean difference for the number of errors committed per month between the two populations. Second, we compute the margin of error. It has two terms, the ZCI and the amount of sampling error in the study, the SEM. In this case, the computation comes out to be 1.96. In the next slide, I'll explain why. When you're computing a 95% confidence interval, the ZCI will always be 1.96. As the figure on the right shows, the z-scores that bracket the middle 95% of all z-scores are negative 1.96 and positive 1.96. So when you're producing a 95% confidence interval, that ZCI will always be 1.96. The second term you need for the margin of error is the SEM, or the amount of sampling error that you expect to have in this study. It's the population standard deviation divided by the square root of n. In this case, it comes out to be 1. You plug this into the MOE equation, and you're going to find that the margin of error in this example comes out to be 1.96. Now that we know the point estimate and the margin of error, we can compute the upper bound and lower bound for this confidence interval. The upper bound value comes out to be 0.46, and the lower bound value comes out to be negative 3.46. Keep in mind what we're trying to do. We're trying to estimate the mean difference in errors committed by these two different populations. The upper bound is the highest plausible mean difference, and the lower bound is the lowest plausible mean difference in errors committed by these two populations in a month. And as will always be the case, the point estimate is exactly in the middle of the upper bound and lower bound values, and it is the most plausible mean difference in errors committed by these two populations in a month. The figure on the right of your screen will help you visualize why the upper bound is the highest plausible mean difference, why the point estimate is the most plausible, and why the lower bound is the lowest plausible value. The curve on the right is the distribution of all possible mean differences. Notice that it's centered on negative 1.5. That's the most likely mean difference. That's the point estimate. You know it's the most plausible because that's where the peak of the curve is its highest. If you look to the lower bound or to the upper bound, the curve goes down substantially. So again, those are less plausible values. They're still considered plausible, but they're considered less plausible than values closer to the point estimate. When interpreting confidence intervals, it's also worth noticing if 0 is located between the upper bound and lower bound on the number line. In this case, you can see that 0, while far on the right, is still within the range of plausible values for the population parameter. So that means that it's plausible that these two populations do not differ in the number of errors they commit per month. It's most likely that they commit a difference of 1.5 errors per month, with the trained employees committing fewer errors, but it's plausible that the difference is actually 0. After you've attained the upper bound and lower bound values, it's important to interpret them. From this 95% confidence interval, we've learned that we can be 95% confident that the mean difference in errors per month is between the trained population making about a half an error more per month to the untrained workers making 3.5 errors more per month. While it's plausible that the training doesn't make any difference at all, because again, 0 is in the range of plausible values, the most likely mean difference is that the trained population makes 1.5 fewer errors per month. In the previous example, we used a z-curve to compute the confidence interval. In this example, we're going to use a t-curve to compute the confidence interval. Most of the procedures are the same, but there are a few important differences. First of all, we're going to use a t-curve here because we do not know the population standard deviation, or sigma. In this research situation, we're trying to estimate the mean difference between two populations, specifically the mean difference in the number of text messages one partner sends to another from the married population compared to the unmarried population. We're going to take a sample of 61 married individuals, and we found that their average number of text messages sent was 31, with a standard deviation of 11.72. The population of unmarried individuals sent their partner, on average, 38 text messages. Most of the computational procedures are the same as in the previous example. You compute the point estimate the same way, the sample mean minus the population mean. There are a couple differences when it comes to computing the margin of error. First, when you're computing the standard error of the mean, or the expected amount of sampling error, you have to use the sample standard deviation rather than the population standard deviation, again, because you do not know the population standard deviation. The other difference is that you have to use the Tci rather than the Zci. And I'm going to explain on the next slide how that works. In the previous example, you used the Z curve, specifically the ZCI. And the ZCI is always 1.96 because the Z curve never changes shape. In contrast, the T curve does change shape based on sample size, as the figure on the right reflects. The larger the sample size, the closer the T curve is to a normal curve. So the larger the sample size, the closer the Tci will be to 1.96. But as the sample size gets smaller, it's going to deviate further from that value of 1.96. In this case, the sample size is 61. That means we have a degree of freedom of 60. And our Tci is going to be about 2. Having a Tci of about 2 means the middle 95% of all t-scores are going to be between about -2 and about +2. Now, how do you find the exact Tci value? You got to make sure you look it up in the correct table. Make sure you're using a two-tailed table and you find the DF. You can see this in the cutout I have on the screen. If you find the DF of 60 and you go over to an alpha value of 0.05, you'll find that the Tci is 2. Now that we have all of the components, we can compute our point estimate and our margin of error. Our point estimate again was -7, and our margin of error was about 3. Using the point estimate and the margin of error, we compute the upper bound to find it to be about -4, and we compute the lower bound to find it to be about -10. Here again, a figure will help us visualize what the upper bound, point estimate, and lower bound values actually represent. The distribution on the right is the distribution of all possible mean differences when you have a sample size of 61 or a degrees of freedom of 60. The peak of the curve is exactly centered over the point estimate of -7. And as you move away from that center of -7, the probability of that mean difference represented as you move farther away is less likely, is less plausible. Again, it's a good idea to identify where 0 is relative to the confidence interval. In this case, 0 is well outside of the confidence interval. That means that a 0 mean difference in text messages sent per month is not a plausible outcome. Based on the 95% confidence interval we just computed, we can be 95% confident that the married population sends between 4 fewer to 10 fewer text messages to their partner per month than the unmarried population. A 0 mean difference between these two populations is considered a not plausible mean difference because it is outside the range of the confidence interval. If you're interested in reading more about confidence intervals, this is an excellent resource. If you're interested in learning more about statistics, visit us at learnstats.com.